Right, I'm going to go through simply supported beam with a uniform load on it. So if we redraw the diagram to show all the forces, so this is uniform load, W. We're going to look at the moment at any distance x along the beam, total length of the beam L. The reactionary forces will be this, because the total force down is W times L. And we've got 2 points, reactionary forces, so they're going to be divided by 2, and they're equal and opposite. As this is a static calculation, there's a formula for the moment. So we're going to look at it at a section at an x along the beam. So if we redraw it again, so this is going to produce a moment turning this way, which is going to be a positive. I've drawn it in the positive direction. So the positive axis will be this force here at this distance. So that's what I've put here. But we've got this uniform load along that little length. Now the uniform load will cause the equivalent of a point load in the middle at a halfway along, and that point load will be the equivalent of W times x at a distance of x divided by 2. So now we can start working out our formulas to get the maximum deflection and maximum angle it could be, the beam could be at. So I'm going to rewrite the equation over here. So EI squared over dx squared, as that's equals the sum of all m's, equals WLx over 2 minus W. I'm going to just do that as x squared over 2. Now we're going to integrate and integrate again. So the first integration is going to be dy dx I equals Lx squared over 4 minus W to 3 over 6 plus C1. If we integrate again, so EI, so that'll be for our angle at any point of x along beam. We've still got the unknown of C1. And this will be for our displacement. So WLx to 3 over 12 minus Wx to the 4 over 24 plus C1 times x plus C2. These are constants and unknown. How we find them out is we can look at our boundary conditions. So for these, our boundary conditions are going to be, so I'll write them up here. So for the angle, we know at the midpoint, because it's uniform load, it's going to end up bending like this. So that the point at the midpoint down there is going to be a tangent, it's going to be horizontal. So the rate of change of y over x is going to be 0. And that happens at a half L. So at x equal to L divided by 2, dy dx equals 0. Now we also know that these 2 points don't move. So y is 0 when x is 0. So when x equals 0, y equals 0. So first thing we can do, we can put this into this equation, and if we put this into this equation, that becomes nothing, that becomes nothing, that becomes nothing, that becomes nothing. So C2 must equal nothing. Right, now the next one. So we're going to substitute these into this equation here to find out what C1 is. So if that's 0, we can get rid of that side, and we can go 0 equals W, and then put all squared over 4 minus W cubed over 6 plus C1. So now we've got kind of one unknown with respect to L, which is what we want. So what we need to do now is simplify this. So 2 squared is going to be 4, 4 times that is going to be 16, and then we're going to be left with L to the power 3 on the top. So what we've got is W L to the power 3 over 16 minus 2 cubed is 8, 8 times 6 is 48, so we get W L to the 3 over 48. Now we need to sort this out, so we can do this. So I'm going to change that to 48, and that becomes 3 plus C1. So what we've got is so we can rearrange this for, I'm going to put C1 over the other side, C1, so that is 2 over 48 WL to the 3, which equals WL to the 3 over 24. So that's what C1 is. And now I'm going to rewrite this equation up here and this equation up here. So we have EI dx over 4 minus over 6 plus 24, and for the other one I over y. Now these will be considered to be a general formulas, so this will give us answers for any value of x along the length of the beam. Now what I'm going to do is work out a formula for the maximum angle it could ever be and the maximum displacement it could ever be. Oops, yeah, that's negative. As we put that over the other side, we have to change around these because that would be negative. So z1 equals negative omega. Good job I got that. Otherwise it wouldn't work. Right, so there's the formula written. I'm going to leave it up there. Now for maximum, y maximum will happen obviously at this midpoint, which is going to be a half L when x equals a half L, and our maximum angle will obviously happen at the 2 points here, so we can do x0. So let's start this. So do it for dy dx max and when x equals 0. So we're going to rewrite this equation. So dy dx max ei equals, that becomes 0, that becomes 0, minus omega L over t 4, which we can rewrite as dy dx max minus omega L 24 EI. Okay, so if you go in and find a formula for that, you can check that out to make sure that's right. Pretty sure it is. Now I'm going to find out for the maximum displacement. For maximum displacement, so y max happens, if we look back here, y max happens at when L is at midpoint, so when x equals L divided by 2. When x equals L divided by 2. So I need to rewrite this formula here. So EI over y max equals, and then what I'm going to do is L divided by 2 to the power 3 over 12 minus W 2, oops, that's to the power 4, yeah, but it's done to the power 4 there, yeah, because it's to the power 4, I didn't carry it down, so I've just caught myself, done a double check. The reason that I was checking myself is because that is going to be to the power 4. We must have things like L on the same order of magnitude. I mean, there's a lot of indices at all times. It's a good double check when you don't have the same to go back and check, see and find out what your error is. That's what I did just then, and that's why I found out that that should have been to the power 4, and I'd made the mistake there when I'd copied it down from up here. And that's over 6. I'm just going to do a double check. And I've also missed out the X there. Seeing that. And I've missed out that because that is 24. So, by going back and doing a double check, I find errors in this formula that I've written out here. Minus omega squared 3, that'll be L over 2. So as you can see, all the L's are going to come out as to the power 4, which is what we want. 24. So this equals 4. Omega L, and that's going to be to the power 3, 8, 12 times 8, cross that out, put a 4 in there, 4, so that's 16, 24 times 16 minus 4, and that's going to be 24 times that 2, so that's 48. Now that is 384, that's also we can make that 384 if we put a 4 up there, and I can make that 384 if I put an 8 here. Now that goes to minus omega L to the 4 over 3, 8, 4 E I Y max. Now I'm going to rearrange for y max equals minus 5 to the 4, 3, 8, 4 E I. Now that is, I did look it out earlier, and that is what we want. So as you can see, it's quite easy to make a mistake throughout this calculation, and that's just because I've done it early in the morning and copied wrong down there. So a simple mistake can cause quite a big error down the end. So always go back and check when you do your work. Okay, thank you.